In this section, we're going to look at the factors that affect the structure and the stability of binary ionic compounds. And the main way that that is measured is in terms of a property or an amount of energy called the lattice energy. And we'll talk about what that actually means. So there are a couple of ways that we represent these binary ionic compounds. One way is through this kind of an array, which is a little misleading because it implies that the ions are actually separated from each other. This is a more accurate sort of representation, the space-filling model, and it shows both the relative size of the ions and also their orientation in a three-dimensional structure. So lattice energy is calculated with this formula, and it is equal to a proportionality constant, the product of the charges of the two ions, so that would be like +1, +2, -1, -2, and R is the distance between the centers of the cations and the anions that make up the binary compound. So these are examples of the types of questions that you might be asked about lattice energy, and it's not like you make an actual calculation, you just are comparing one structure to another. And when you have the question that says has the most exothermic, so what that means is when the ionic compound forms from gaseous ions and they come together, that energy is the lattice energy, and that's an exothermic reaction. So remember, we said previously when we were talking about bonds that when bonds form, and this is kind of like a bond forming, then that's going to be exothermic. All right. So if we look at lithium fluoride and we compare that to cesium fluoride, so what is the relationship there? Well, the charges are in both cases going to be +1 and -1, so that's not going to really have an effect. But what is different is that lithium is much higher on the periodic table than cesium, and it means that the distance, which is R in the formula, is going to be less for lithium fluoride. So that means it's going to have a larger lattice energy. So you should probably stop the video and see if you can think through yourself what the answer is for the next one, but I'm assuming that you will have done that. So it's a similar sort of comparison. In this case, the positive ion, sodium, stays the same, and the negative ions are different. So we're comparing the bromide ion to the iodide ion, and iodide is a larger ion than bromide. So that means that the NABR is going to have a larger lattice energy. For the next one, we have barium chloride and barium oxide. So the barium is the same, and then if we look at the chloride ion, so that's what, 2 negative charges, and with oxygen that's also a -2, so that part is also the same. So the only thing that we're kind of dealing with there is the size of the ions again, and oxygen is higher and to the left of chlorine, so that means that it's going to be smaller, so we would expect that barium oxide would have a higher lattice energy. For the next one, somewhat similar, we're comparing two sodium ions, so that's a +2 charge, with a +2 charge for calcium, and calcium is lower and to the right, so we're going to assume that calcium is going to be larger than the sodium ion. So that means that sodium sulfate should have the higher lattice energy. On the next one, we are comparing K and 2K, or K2O, sorry. And then for the negative ion, we're comparing fluorine and oxygen. So fluorine is going to be a little smaller then the fluoride ion is going to be a little smaller than the oxygen ion. But in the second case, the K2O, we have +2 charge and -2 charge, so that's going to make the numerator in the expression larger, so that's going to mean that that's the larger lattice energy. And then for the last example, so there we have the charges all balance out, so it's +2, -2 in both cases. So then we're comparing the positive ion size, which is lithium and sodium, so the lithium is smaller, and also the oxygen is going to be smaller than the sulfur. Okay, so that means that Li2O should have the higher lattice energy. So we can think about the process of an ionic compound forming as a series of steps. So for example, with the, let me just get my pen here. So for the first step with the metal changes to a gas, so that's an endothermic reaction. Then the atoms in the gas are ionized, so that's endothermic, meaning it takes energy. And then for the nonmetal, assuming that that's, in this case, a diatomic gas. So the diatomic gas has to first form individual atoms. And then in the next step, we have those atoms gaining electrons. So that's going to be an exothermic reaction. And finally, we have the step which involves the two ions, the metal ion and the nonmetal ion, coming together to form the ionic compound. And that's the step that actually is represented by the lattice energy. And that step is always going to be exothermic. All of those steps that we just discussed can be represented in a diagram like this one. So if you sort of follow through, you can see all of the different steps, that are involved. So for example, in this step, this is the metal going from the solid form to the gas form. This is the metallic atom losing an electron. And then this next step is the diatomic gas molecule breaking up into individual atoms, and then the atom here, so this would be the fluoride ion gaining an electron, and then finally these two ions, so the Li plus and the F minus, coming together to form LiF. This is, I don't know if they say it in here, this is sometimes referred to as a Born-Haber cycle, so that's the name that's given this. In more advanced chemistry, you actually would talk about this more, but I don't think for our purposes that you need to know really much more than this. So I may have included a few more slides, but I think that we'll probably be safe just to understand this much of this particular process. Yeah, so that's what I've shown in this slide. If you're given all these different values, the lattice energy, ionization energy, etc., then you can find the delta H formation. So if you sort of flip back to the slide that shows that, you're essentially looking for that one missing value when you know everything else. And so it's not hard to do, but I don't think that that's something that's actually tested on the AP test. Yeah, this is a similar type of problem. Maybe in class we'll do one of these just to sort of get the idea, but it's not difficult. It's just a matter of keeping all the steps and the signs of whether the reactions are exothermic or endothermic straight.